So my name is Dale Anderson, and as Anna said, I'm a clean fuels engineer at the National Engineering Laboratory. And today I'll be discussing the impact of uncertainty on industrial flow measurement. So just a bit on what I'll cover today. Initially a bit on basic uncertainty theory and the terms that are usually here bandied about when discussing uncertainty. The potential cost of errors in industry with a few examples. Also going to discuss different types of uncertainty, so type A and type B uncertainty, and how we select which type it is and how we use each sets of data accordingly. I'll also discuss uncertainty calculation stages, so if we're trying to calculate the uncertainty of a particular parameter such as flow or something like that, how we would do it. And I'll finish off with a few practical examples that are common to us. And all of the first four sections should lead nicely into the practical examples to just give a feel of what we do. So the first point to note is, in terms of making measurements, that measuring instruments only give an estimate of the true value, and they don't give the true value itself. As it says here, the true value is unknown. So if you think everyday items such as stopwatches, thermometers, your scales in your kitchen, anything like that is just trying to give an estimate of the true value. And the true value, as I said, is unknown. So what is uncertainty? And when we talk about uncertainty, what is it? So it's an interval either side of the measurement result which we expect the true value to lie with a given confidence, and this is important. So as you can see here, you've got your indicated value on your chart, you've got your associated uncertainty, bands either side of this, and your true value is expected to lie somewhere within here with a given confidence level. So I spoke about confidence levels a bit in the slide before. This is a likelihood that a real value of a measurement will lie within a specified interval. The larger the interval, the higher the confidence level the true value will lie within it. So, for example, here, the white section here, you could say, possibly quote a 60, 70, 80% confidence level in the white section. If you want to have a higher confidence level, say 95 or 99%, you need to increase your uncertainty interval. And that makes sense. If you want to have greater certainty that your value will lie within the interval, you need to increase the size of your interval. So when you state a result from a measurement, what should you define? So you need to define three things. You need to define the measured value, so that's what's read out. The uncertainty associated with that measured value, which you calculate, and the associated confidence level that the measured value will lie within. So as it says here, the result of a flow measurement may be stated as 3.5 plus or minus 0.2 litres per second at a 95% confidence. So what does this mean in reality? It basically means we're 95% confident that the value will lie somewhere between, the true value will lie somewhere between 3.3 and 3.7. Error, that's a term you hear often. So what is error? It's defined as the difference between the true value and the measured result. It will of course be unknown, and this is because we do not know the true value. You do hear error or error values stated. This is commonly when you use some sort of highly accurate or very low uncertainty reference instrument to compare the results with an instrument under test. So you will compare the value from the instrument under test to a highly accurate reference, and you may quote an error, but it will be in comparison to a reference, which again, that true value is not known, but we know it's close to the true value. Accuracy is another term that's used. This is the closeness of agreement between the result and the true value. You can have an accurate measurement with a larger uncertainty. However, you can't attach a value to accuracy, and it's a qualitative term. So you can describe something as being highly accurate or not very accurate, but you can't assign a number to it. When you start assigning numbers to things, that's uncertainty, not accuracy, and you need to quote a confidence level with your uncertainty. Also repeatability, that's another term that's commonly used. And this is a closeness of agreement between successive measurements under the same conditions at the same time. So how many times can your instrument give the same reading over and over again when it's done under the same conditions at the same time? So as it says here, good accuracy means good repeatability, because if it's accurate, it needs to be close to the true value all the time, and to do that, it needs to be repeatable. Poor repeatability means poor accuracy. So you can have something that, for example, one instrument may give a result very close to the true value once, but it won't do it consistently. So if it's got poor repeatability, it's got poor accuracy. And finally, good repeatability does not necessarily mean good accuracy. So the results could be very close to one another repeatably, but they could be far away from the actual true value itself. Another term that's used is bias. This is described as every measurement being affected in the same way. So it could be clocks over or under reading, or running fast or running slow, or scales being out by a given amount under or over. You can correct for bias, but you need to consider what the uncertainty is in your correction of the bias. So that just sums up basic terms that are commonly used in uncertainty theory. So I'll go into a bit about the cost of errors and just a couple of examples in industry where we need to know flow rates or values to a low uncertainty to ensure that we're not exposed to large costs. So just a fact from 2019, on average, 81 million barrels of oil were produced per day at a total cost of 5.19 billion. If the uncertainty in the amount produced is 0.25%, so 0.25% of the 5.19 billion accounts to £13 million per day, and which isn't an insignificant amount of money for both oil producers as well as governments in terms of tax revenues as well. So this really highlights the need for low uncertainty measurement in industry. A more relatable example for us possibly is the uncertainty at petrol stations. So an uncertainty of 2% at a 95% confidence level, and assuming a tank of 50 litres, the uncertainty in filling the tank would be 50 plus or minus 0.1 litres at a 95% confidence level. So this essentially means that we've got 95% confidence that the volume of petrol or diesel, whatever you fill your car with, is between 49 and 51 litres. And assuming a cost of £1.15 per litre, the uncertainty in the cost of filling is £1.15. So in assuming you fill your car once per week, this can leave you exposed to up to £59.80 per year. So I'll go on now to touch on the types of uncertainty and how we assign uncertainty values to parameters in practice. So there are two main types in terms of assigning values or calculating values. There's type A, where we use real data, or type B, where we may rely on information from manufacturers or calibration certificates, or even our own judgment at times to assign uncertainties to various parameters. So if I start with type A, so this really comes from the analysis of repeat measurements. We know that repeating a measurement reduces the chance of errors, and subsequently repeats never agree. So how do we know which value to use from all this data, and what does the variation or the spread of the data actually tell us? First of all, there's a number of points here. How would we get the best estimate of the true value? So we would take the average of the points, but again, this is an estimate, a best estimate of what the true value would be. How would we determine the spread in values? So we could take the highest and lowest point and calculate the range, but this doesn't do anything in terms of characterising what's going on within the range and how spread the values are within the range. And as it says here, it ignores the majority of the data. So what we tend to do is calculate a standard deviation, and this really characterises how spread out the numbers are. So if we illustrate with an example, suppose we take 10 readings of a flow of oil and get the results in the table below. To calculate the standard deviation, we would take the average of all of the points and then subsequently work out the difference between each point and the average. So this is shown in the green row, the difference between all of the points and the average. You then square each of these differences together. As it says here, we need the size of the difference, not the sign. So if you square a negative or positive number, it's a positive number. We would subsequently take the sum of the squares and then take the average from there, or n minus 1 from there. Then from that value, we would take the square root. So what we've essentially done there is calculated the standard deviation for that data set or that sample, and that represents the standard deviation of the population, and that using that equation there. So each of the steps shown in the equation in the bottom left, that's what we've essentially did there. We've taken the difference between each of the values and the mean value, squared it, summed it together, divided by the number of values minus 1 and taken the square root of it. So what does this value actually mean in reality? So this is our values here. We don't have a lot of data currently, but we know that data tends to cluster in distinct patterns. So as we gather more data, you can see a pattern start to emerge. And what you tend to get when you take measurements are a lot of things in life, such as people's weight and people's height and things like that. You get this characteristic bell-shaped or normal distribution or Gaussian distribution curve, where most of the values are centered around the true value, and then it tails off either end and the frequency decreases. Expanded uncertainty is the uncertainty at a higher confidence level than the standard uncertainty. The likelihood of finding the true value in this interval is typically, it says 95%, but you can make it any value you want depending on what coverage factor or what factor you multiply the standard uncertainty by. So for 95%, the expanded uncertainty is equivalent to 1.96 standard deviations. And it's typical to use expanded uncertainties when quoting results because we want to have more confidence in the fact the true value will lie within the limits that we're stating. So that's why we do that. And as I said previously, you can select whatever confidence level you want for a normal distribution and multiply it by 1.68 for 90 or up to 2.58 for 99 and all intervals in between as you desire. So now I've been over type A uncertainty analysis. So if we look at type B, as it says here, not all uncertainty comes from type A analysis, and we often need to assess this from other sources. So it could be purely using judgment or past experience. Manufacturers may provide data or provide tolerance levels for things they provide, or we may get a calibration certificate for something that's been calibrated. What we tend to see is from this data for sort of tolerance levels or calibration certificates, or even using their own judgment, it's usually in the form of an expanded uncertainty value that we get initially. So we need to consider the use of a coverage factor to convert that back to a standard uncertainty. So to get back, it's just the opposite process. So if we want a standard uncertainty, we'll take our expanded uncertainty from a relevant type B source and divide by the appropriate coverage factor, depending on whether it's normally distributed and what the confidence level is. And again, just to repeat, to convert expanded to standard, you need to know the distribution. So for repeat measurements, if you know things, the uncertainty quoted is based around a normal distribution, you can use standard uncertainties, or you can use the relevant coverage factor for the confidence level. And this is just, again, repeating it. So coverage factor may be given on a calibration certificate, so it may quote the result plus or minus a given uncertainty for it, or it may give you the coverage factor. But if it gives you the confidence level, we can get the coverage factor from a lookup table or something similar like that. So sometimes we don't always assume normal distributions, and we don't have the data to assume that. So if you know the value lies somewhere between two limits with equal probability. So examples here, it says our instrument resolution and acceptance criteria. So when things are made in manufacturing processes, for example, they will meet a given standard if they're between two values, but there is not necessarily a normal distribution of the values, and we can't assume that, so we would use a rectangular distribution, and this is calculated. A standard uncertainty is calculated as the difference between the upper limit and the lower limit divided by root 12. So taking resolution uncertainty as an example, so if we have some flow meter its resolution uncertainty is just the two significant figures in no decimal places, really, the value here could be anywhere between 34.5 and 35.5, and it would still read 35. And it's no more likely to be at 35 than 34.5. So in this case, we would assume a rectangular distribution and calculate our standard uncertainty through this method. So as you can see here, we've got our upper limit, our lower limit, and divided by root 12 to get our standard uncertainty in the resolution. If we want to reduce a resolution uncertainty, we can give the value to one decimal place. So now, instead of between 34.5 and 35.5, it can be anywhere between 35.05 and 34.95, which reduces the uncertainty by an order of magnitude. So now we've discussed the types of uncertainty and how we tend to calculate standard uncertainty for various parameters. I'll go through what we tend to do when we're constructing an uncertainty budget for a particular parameter or value that we want to calculate. So first of all, we identify all of the uncertainty sources that we think contribute to this parameter. So for using an equation to calculate something, so all of the factors that are in the equation, or all the terms that are in the equation, we need to assess whether these have uncertainty or whether we need to calculate uncertainty for these. We then estimate the magnitude. Again, this may be we may need to look at the data and use type A analysis, or maybe it's just judgment, or we're using manufacturer's tolerance levels or something like that to calculate, so it's more of a type B analysis to estimate the magnitude. We then convert these to standard values, so sometimes you get them in the form of expanded uncertainty, so then you need to consider the distribution, the confidence level that's stated for the expanded uncertainties to convert this back into a standard uncertainty value. We then calculate the sensitivity coefficient. I'll touch on this more in the example, but it's looking at your current standard uncertainties are quoted in the units of the current parameter that the uncertainty is you're quoting in. So we need to consider how sensitive our desired final uncertainty parameter that we're calculating in is to the current parameter. We'll then convert them to output values, so we multiply the standard uncertainty by our sensitivity coefficients. Estimate the degree of correlation. So sometimes our measurements can be correlated, so we need to recognise that. So for example, if we are using two thermocouples that have been calibrated using the same reference device, we need to take into account of that, because they can be both out. If the calibration device is out, it's going to be out both the same way for both devices that have been calibrated using the same calibration device, and we need to consider that. So correlation is very important. Combine the uncertainties using the appropriate method, so depending on whether they're correlated or uncorrelated, and I'll touch on this more in the example. And then finally, express the uncertainty at the correct confidence level. So your final result will tend to be stated in standard uncertainty, but if you want to have a greater confidence level in the result, you'll need to multiply it by the appropriate factor. So now we'll just go through a few examples that will hopefully tie this together a little bit, and it'll be hopefully quite useful. So first of all, we can look at the example of an orifice plate, which is used to measure the mass flow rate. So it's just a simple device where it's got a smaller diameter orifice installed in the line, and we can use the pressure differential across this to measure mass flow rate. So the equation you can see in the blue box below can be used to calculate the mass flow rate. The equation itself and the derivation itself is quite unimportant, but for this particular webinar, but what you need to look at is each term within there. So your discharge coefficient C, your beta because it's D2 over D1, your expansibility factor, D squared, delta P, and the density, the upstream density. All of these values will have uncertainties associated with them, and we need to work out how this contributes to our overall uncertainty and mass flow rate. So if we go through the steps we talked about previously, so the first is identify all the parameters that will have an uncertainty contribution. So we go through each of them: the discharge coefficient, expansibility factor, what the pipe diameter and orifice diameter is, what the pressure drop is, determined by the YouTube manometer, as well as the density of the fluid. So all of these parameters will have an associated uncertainty, and this will affect what the uncertainty of the calculated flow is finally. So the second stage is identifying what the uncertainty values are. So for the first two, which are highlighted in green, the discharge coefficient and the expansibility factor, they can be quoted as a percentage uncertainty. So we would get them from a percentage to an absolute uncertainty by just taking into account the value of these and multiplying it by it. Sometimes you may get quoted as absolute uncertainty, such as the pipe diameter and orifice diameter. So they can be quoted as, I think that's 0.1 mil and 0.01 mil uncertainty, expanded uncertainty for the pipe and orifice diameter. And the pressure drop and density uncertainty values, these have been highlighted in red just because your pressure drop will be calculated by working out the difference in height in the YouTube manometer. So you need to feed into this value to get the 100 value. There's a separate calculation, so you'll need to work out the uncertainty in the determination of the height difference, the uncertainty in the density of the fluid that's used. So this is just to highlight that a separate uncertainty calculation is sometimes required to feed into this, and the same for the density of the fluid. This will be, the density is dependent on the pressure and temperature. There will also be some sort of equation fit to calculate the density, and the uncertainty of the equation fit, the temperature and the pressure needs to be taken into account to calculate the density here to feed into this calculation initially. So stage 3 is looking at the converting to standard uncertainties. So as you can see, for the discharge coefficient, expansibility factor, pressure drop and density, a coverage factor of 2 has been assumed, so this may be stated, or we may know this information. So you can divide by a coverage factor of 2 to get the standard uncertainty. The 1.73 values, so this is half of the root 12, so this is assuming a rectangular distribution. So Possibly these pipes have been purchased from manufacturers and have quoted tolerance levels for the orifice plate and also the pipe diameter. So in that case, we would assume a rectangular distribution and calculate our standard uncertainty through that method. So stage 4, we're looking at calculating the sensitivity coefficients. So what this is, it's working out how sensitive the flow rate is in the equation above, so Q, to a small change in each parameter. So for discharge coefficient, you're looking at how sensitive Q is to a change in C. And there's different methods you can do this by. If the equation is relatively simple, you can differentiate the equation, so dQ by dC, and you can add the values for all of the other parameters to calculate sensitivity coefficient. And the units of this sensitivity coefficient will be the units of flow rate, so kilograms per second in this case, divided by whatever the units of the quantity you're analysing are. And what this does is it works out how sensitive the parameter is, and it changes the units of standard uncertainty for that particular parameter into the units of kilograms per second for Q. So now we have all our output values UC. We can then look at calculating the uncertainty for the flow. So one method you could think of doing this, you've got all our uncertainty values, you could quite simply add all of these numbers together and get an overall uncertainty. However, this value would tend to be larger than would be realistic, because it's not realistic that all of the values are going to be out significantly all of the time. So we need to take into account of that. So the typical method to assess this is we use the root mean squared method for uncorrelated measurements. So what we would do is we would take the UC term in the purple column and square it for each parameter. We would then sum all of these values shown in the point down at number 7. So the 0.0711 is the sum of all of the UC squared values. And then we would take the square root of the sum of all of these values. From there, we know our sensitivity coefficient is 1. We can work back. Our standard uncertainty would be 1. If we want to quote a coverage factor of 2, so just over 95% confidence, we multiply it by 2 and we would get an uncertainty of 0.533 kilograms per second. So that's how we would tend to do things. So another example is looking at the volume of the tank. So the volume of a storage tank can be defined as pi d squared times height divided by 4. However, we want to calculate the volume of the tank at 15 degrees, and we need to take into account the thermal expansion of the tank. So if the measurement was carried out at a higher temperature or lower temperature, we need to take into account of that, and this equation takes into account of that. So the pi d squared h over 4 is the V measured, and then we take into account this by using some thermal expansion coefficient as well as the temperature measured to calculate what the volume would be at 15 degrees. So again, we just go through the same process. We identify all our uncertainty sources, noting this time, which is quite common, so for one parameter, just the diameter that we're measuring, you can have more than one uncertainty, or it's almost always common that you have more than one uncertainty source for each parameter. So the calibration of the instrumentation that's used to determine the diameter, the actual determination of the diameter, how this may drift over time, are factors that we need to consider in the uncertainty budget. We go through the same method again, so going from expanded uncertainty, understanding the distribution or quoted coverage factor, calculating the standard uncertainty, then through to calculating the sensitivity by either differentiating the equation or making small changes in one just to see how sensitive it is, multiplying the terms together, squaring the terms, taking the sum of the squares, so at the grey box in the bottom right, and working our way back through again to give an uncertainty of 3.188, a coverage factor of 2. So now, just as an example, what if we think that this value, this uncertainty value, is unacceptable? We think this is too large and we want to reduce it. So we can get the greatest effect in reducing uncertainties by looking at the UC squared term and reducing those parameters because they are having the highest contribution to the uncertainty. It wouldn't be of much use to look at reducing, for example, time drift in the height or time drift in the diameter, because they've got lower contributions, so the effect of reducing them would be much less. So the first thing you look at is the calibration in the diameter. So the easiest thing would be to try and reduce that. So if we reduce that, you would see a reduction from 3.1 or 3.2 to 2.7. If that's still not high enough, you look at the next term and try and reduce that down again further. So again, looking at the calibration in terms of the height, you can try and reduce that, and that will reduce even further. And then finally, looking at the determination of the diameter, can we reduce that? And this brings the value down further. So the key point is, if you want to try and reduce your uncertainties, you look at your largest contributions in the UC squared terms and try and bring those down. Finally, so all of these examples I've spoken about previously are relatively simplistic in the sense that they've assumed that they are uncorrelated. So this is when the measurements are independent, and you can see that they could be at different parts of the uncertainty range, and that's why we can use our root mean squared method. So showing an example here, we've got two different flow rates where the true value for U1 is less than the indicated value, and for U2 is greater than the indicated value. And this is just showing that these measurements are independent. And in this case, we can do what we did in the examples. We can square each uncertainty term, take the sum of them, and take the square root of the sum to give the overall combined uncertainty. So however, for correlated measurements, so for example, measurements made by the same meter, if the meter that you're using underreads for one reading, it's going to underread for every reading. So using the root mean squared method isn't appropriate because it won't give you a realistic sense of how the uncertainty is. So for this, the uncertainty of the combined flow, we use a sum of the uncertainty in 1 and the uncertainty in 2 to give our overall uncertainty. So how does this work in practice? So if we go back to the example of the tank volume, the first example, this is the slide from the first example, all of these have been assumed, values have been assumed to be uncorrelated, and we get an uncertainty in the volume of 3.188, which was before. So now, for example, if I say, if the height and the diameter were determined using the same instrument, and this instrument is going to be calibrated or using instruments that have both been calibrated using the same calibration standard, these values will be correlated for calibration, because if the calibration equipment that's used to calibrate these is out, it's going to be out the same way for both, typically. So how would we treat this? An example for a budget. So if we look at the terms in red here, our calibration diameter and calibration height. So rather than square these terms, what we would do is we would sum the 0.955 and sum the 0.905 initially, and then square the sum of these values. And then we can continue with our calculation as we normally do. What you can see here, if you go look at the final value of 4.136, is this value is larger than the initial 3.188, and this makes sense because if your value is going to be over or under a certain way for the height and diameter, the uncertainty is going to be greater in the fact that they're correlated because they're both going to be out the same way. So just a summary on handling uncertainty calculations. Always convert to standard uncertainty before performing your calculations. Ensure that all your units are identical. So this is by converting your standard uncertainties in the units they currently are and applying the appropriate sensitivity coefficient. Always round up and keep asking. One good thing, one of the best judges in this is asking whether this feels right. Does the value that you've calculated look about right for what you think the uncertainty would be in this? A bit on further reading. So the guide to the expression of uncertainty in measurement, this really goes in a bit more detail than the topics I've covered today, which just almost skims over what's contained within this. This has been published by a consortium of international standards bodies and is recognised generally as providing standard methods for uncertainty analysis. And then finally, just to summarise, measurement is meaningless without a statement of uncertainty and associated confidence level. Assessment of uncertainty can be time-consuming and it requires careful thought, but ultimately, if it's done well, it will save time and money in the long term, particularly for high-value applications. And thanks for listening, and I'll take any questions, I think, Anna. I've got time for questions.
Thank you for that, Dale. Yeah, I think we've got time for a couple of questions. So let me have a look what's come through. So the first one is, what do you believe the main challenges are in uncertainty analysis?
Okay. So I think I would probably say 3. I think making sure that you consider all of the uncertainty sources that may be contributing. So what environmental effects are having, and for example, looking at, for instrumentation, looking at drift, what the calibration uncertainty is, what the resolution uncertainty is, and other factors. So actually understanding, and you need to have knowledge of the system, not just knowledge of uncertainty to properly assess this. Also, and again, this feeds into not having knowledge of the system. In the absence of vast majority or a lot of data, how do you estimate the magnitude of these sources? So looking at type B analysis, you need to speak to people who have been involved in the process before or know the process well to look at that. And also another one is treating correlation correctly. A lot of the instruments we have are calibrated using the same source, and sometimes we have multiple instruments on the one facility that are calibrated using the same source. So treating correlation correctly between measurements as well.
Okay, great, thank you. Hope that answered that question. And let's just go over to another one. I'm quite conscious of time. So what areas or projects are you currently researching regarding uncertainty?
Okay, so all our testing facilities have active budgets. So anything we are testing flow meters in will have an uncertainty on the flow rate for the standard. So these are constantly being reviewed and updated based on recent calibrations, etc., and things like that. We've got some facilities that are currently being built and commissioned, so one for testing domestic gas meters, and we need to essentially build a budget for that to estimate what the uncertainty is for the standard as well. So it's mainly looking at our facilities and what the uncertainties are in them, and ensuring that we consider all of the sources and monitoring them regularly to ensure that they're up to date and accurate.